Okay, it's week 2 Wednesday, and we are talking more Monte Carlo integration. And so on Monday, we wrapped up with this example where we said we can use Monte Carlo integration to estimate the integral of any function. And I kind of want to just go over the same example I did on Monday, and we'll look at another example. And then we'll talk about importance sampling, which is a bit of a misnomer, but, well, that's what it's called. Okay, so we said we can use Monte Carlo integration to integrate any arbitrary integral. Okay, so if we've got some function h of x over some closed interval a, b, we can do this. Now, I'll talk about this later, okay? And the way we approach this is we want to turn this into the form integral or a function times a PDF, okay? Because what we learned that the Monte Carlo estimator, that is the expected value of some function h of x, h applied to random variable x if x is defined by the PDF f, right? So this is kind of the funny notation. We want the expected value of the function h applied to the random variable x where x is defined by the PDF f. We said this thing can be estimated using the Monte Carlo estimator. That is, we just draw random values from this a random sample from that random variable x, we apply the function to it, and we take the average. We take the sample mean. And so we can turn this original problem, the integral of this, into the form of function times a PDF. And the PDF of the uniform distribution is just 1 over a constant. The constant is the width of your interval. So if your uniform distribution goes from A to B, your PDF is just 1 over the distance between A and B. And so if your uniform distribution is the standard uniform going from 0 to 1, your PDF is just 1. But if it's going from like 0 to 7, it's going to be 1 over 7 or something like that, okay? And so anyway, this is in the form of the function h times the PDF, and we can take the integral of this thing by using the Monte Carlo estimator, okay? And so this will give me the average value of the function over that interval going from A to B. And then to get the value of the integral itself, I will then just multiply it by the width of the interval. And that will give me an estimate. So again, the Monte Carlo estimator is you just generate random values from that PDF. In our case, the PDF is the uniform distribution. And we can do this very easily in R because we have R unif. R unif is very simple. We apply the function h to every single one of those values, and then we take the mean. And then we can take that mean and multiply it by b minus a if we want. And that is our estimate of the integral. So let's do this for this function here. So the function that we want to apply it to is just, I don't know, just some arbitrary function. It's a mess. It's a mess. We don't actually want to integrate it. Okay, we could, but we don't want to do this. Okay, but we can do this, and we can just say, all right, here's what the function looks like. Here's the plot of the function, and if I wanted to integrate this, how would I do this? And this is the exact process. We're going to just generate 100,000 values. Okay, set seed is just an arbitrary number. I just tend to use set seed 1, but again, you can plug in any integer into set seed, and that's fine. Okay, so we do R unif. I want 100,000 values. My interval goes from 0 to 1. And what do? We apply that function h, which we defined back here, cosine 50x plus sine 20x quantity squared. So we're applying that function h. So you probably have to write, define h somewhere. This gives us the values ran through h. And then we're going to compute the mean of all of those values. And we get this thing, 0.966,863, which is close to the theoretic value 0.96520. Okay, that's the average value. Then to get the area of the integral, we multiply that average value by the width of the interval. In our case, the width of the interval is just 1. So our estimate of the integral just ends up being 0.966,863 as well. Does this feel okay? Do we have any objections to I just told you this is what we do. But do you feel like this is good or bad? I don't know. Okay, let me go ahead and give you your first view quiz answer for today. First view quiz answer today is the letter D. D as in dog. I feel like we're missing a bunch of students today, but I don't know. Maybe, does it feel less populated? A little bit, right? I won't say my feelings are hurt. And then here I created this little script will just kind of create the plot of how those values kind of settle down, right? So here, if we just take a look at the first 10,000 values, we can look at the running mean, right? The running mean is basically the sum of how many values you've seen so far divided by how many values you've seen so far. And so here, taking the cumulative sum divided by the vector 1 through n, okay? And then this formula comes from the variance of that estimator. And then we're just gonna kind of apply it, going up or down 2 standard errors. And this is it, okay? And so again, we can see it kind of settle. It bounces around a little bit, but again, it wiggles around a lot in the beginning, and then after a while, it kind of settles. Now, the Monte Carlo estimator for a unidimensional integral is actually fairly inefficient, okay? Let me just kind of illustrate what I mean. And this is a little bit, of an aside, okay? But what happened here? Oh no. Okay, let me try this again. I can't see it. All right, so probably when you did calculus, you learned about like a Riemann sum, right? This was kind of like the introduction to an integral. And let's say you had this thing, okay? Okay, so for a Riemann sum, what you would do is you would basically take these rectangles of equal width, and you'd so hard, and you would add their things up over and over. All right, so this is okay, and you would do this, and you would take all of these rectangles, And they're all supposed to be of equal width. And this, if you look at how accurate this thing is, oh geez, okay. All right, just pretend I did this, please. Okay? And if you look at kind of the efficiency of how, the estimate, right? So if you look at I hat versus the actual I, okay? This difference, as a function of n gets bigger, okay? The efficiency, the accuracy of this thing is way better. So the Riemann, if you do this, right? And what is, I don't even know how to spell this. Okay. When you do Monte Carlo, okay, it's just picking random spots, okay? It's going to say, all right, let's pick a spot here. Let's pick a spot here. Let's pick a spot there. Let's pick a spot there. Let's pick a spot here. Let's pick a spot here. And it's taking this value and this value and this value and this value, and they're not necessarily going to be equally spaced out. And it turns out you need a lot more n, you need a lot more values to work with this. And so you might say, well, why would I want to do this? Okay. Well, with a one-dimensional case, the Riemann method, the Riemann sum, is going to give you better performance, okay? But sometimes you work in kind of this, you have no idea what the function looks like, and it might even be in high dimensions. And so in those cases, this Monte Carlo thing where you just kind of draw things at random could actually work out well, okay? Just put that thought on hold, because we'll return to it like in several weeks, okay? I know, it's like several weeks away, but just the idea of doing things in kind of this organized grid search where you just have equally spaced things out works great when you're just dealing with a one-dimensional function. But in a higher dimensional function, in 2 dimensions, your grid has to be a lot more complex. In a 3-dimensional function, now your grid has, let's say you have on a 1-dimensional, you got 1,000. In 2 dimensions, now you have 1,000,000 points. In 3 dimensions, you now have 1,000,000,000 points to do, okay? With Monte Carlo, where you're just doing it random, you don't have to deal with that as many, okay? But again, put that thought on hold. Let's take another look at another example here. We're going to use Monte Carlo integration to estimate the value of a function. And so let's talk about the cumulative distribution function of the standard normal random variable, okay? Now, we already have a function that does this, the CDF of the normal distribution. We just use P norm, right? And then we just say, hey, P norm of 0 is 0.5, P norm of 1.96, 0.975, et cetera, okay? I think in 100B you learned that there is no closed form solution for the cumulative distribution function of the normal, right? And the P norm that your computer uses is actually an approximation. It's not the most accurate thing, okay? It's accurate up to 16 digits in decimal, and that's good enough for us, right? Because as far as double precision goes in the computer, double precision is only accurate up to 16 digits anyway. So P norm gives us an approximation that's accurate up to 16 digits, and we say, okay, well, that's good enough as far as I need. But it's not the actual value, okay? It's just a quick and efficient way to calculate these things. We could say, you know what, let's try to get an answer using the Monte Carlo approach. And again, the Monte Carlo approach, for a lot of things, is the worst approach you can use. and we're like, why are we taking this class? Basically, and I'll probably repeat myself several times, if you can do anything other than the Monte Carlo, you do it, okay? If you can do it analytically, do it, right? If you can do it like a methodical thing, do it, okay? But a lot of times you're just stuck in a position where you don't know what to do, and you think, well, maybe let's just use Monte Carlo, and then you can do that, right? So, trying to estimate pi, you can estimate pi using a Monte Carlo approach, and I think I've got that in one of your homework assignments coming up. Yeah, it sucks, okay? You're gonna get a bad estimate of pi, but you'll see the Monte Carlo approach. Okay, so anyway, we're gonna take the Monte Carlo approach to estimate the normal cumulative distribution function, which is defined as this, all right? So we have the standard normal PDF, okay, defined in terms of t, because we want a function of x, and we're gonna say it goes from negative infinity up to x, and we just want to see what's the area from negative infinity up to x of this PDF. Okay, we have no closed form solution for this. How can we use Monte Carlo integration for this? Okay, so we want to basically, again, we want to turn this function into something where it's in the form of function times a density, and we want to do something like that, okay? So with a little bit of creative thinking, we're going to use this indicator function, okay? We're going to say, let's say if some random value z is less than x, we give it a 1, and if it's not, we're going to give it a 0, okay? And what is the expected value? Okay, the expected value of this indicator function is going to be equal to 1 times the probability of z being less than or equal to x plus 0 times the probability of z being greater than 0, right? Okay, and so if z is a standard normal random variable, then the expected value of this thing is going to just equal the CDF, right? So if we say z is a standard normal, then the CDF of z, of the standard normal, is the function that we want, we can say the expected value of this indicator function is going to be equal to the standard normal, CDF. Does this feel okay here? Okay, and so now that we have the function that we want, right, the standard normal CDF is expressed as the expected value of this function, z being less than or equal to x. Okay, so we're saying we're able to generate values from the computer using the standard, using our norm. And so we're going to say let h of x, the function, our arbitrary function, just be this indicator function. Okay, so we're going to say let's use the computer's ability. The computer is able to, so again, this is this contrived scenario. We're going to say the computer is able to generate random values from the standard normal distribution. Okay, and so far we're just saying the computer is able to generate these things. We haven't even explained how the computer is able to generate this. This is a future topic. But right now we're just accepting the fact that the computer is able to generate values from the normal distribution. Okay, so we're going to generate a whole bunch of values from the normal distribution. And then we want to know, okay, what is p norm? What's the cumulative distribution function for, say, x equal to 0? What proportion, what's the probability that z is less than 0? Okay, how do we get that? Well, we're just going to calculate the indicator function. It's basically just a logical thing. Let's say we generated 1 million values from the normal distribution. We turn this into a logical vector. We take those million values and we say, is it less which values are less than 0? Some will be true, some will be false. And we say, what proportion are less than 0? Okay, so we just ask, what's the mean of z being less than 0? And so if out of the million random normal values we generated, let's say 500,050 are less than 0, then my estimate of p norm, or the estimate of the cumulative distribution function, is going to be 0.50005. So this is going to produce an estimate of the CDF function. So how does this work? All we're doing is we're just converting the indicator function, okay? And that's basically equal to the probability, right? So let me just, so it seems silly, okay? But it works in, sorry. Okay, so all I'm going to do is I'm going to say, okay, let's generate some vector z. Our norm, let's take 1,000,000 values. Let's generate 1,000,000 values from the standard normal distribution. And again, right now we're just treating the ability, we're just taking for granted the fact that the computer is able to generate random values. And then we're going to just say, how many values, right? We can just say, is z less than 0? Okay, we get a vector of true false values, and we can just say, okay, what is the mean of z less than 0? Okay, and we get something, we get 0.4997. So this is the empirical value, and this is going to serve as our estimate of what p norm is. Okay, we can say, okay, well, how many values are less than, say, 1.96? Okay. So again, if you look at z, these are the values of z. We can ask, okay, which values of z are less than 1.96? We get a bunch of trues, some are false. And we can ask, what is basically the proportion of values of z that are less than 1.96? And we get something around 0.975, okay? And that compares favorably to the kind of our true answer. Whoops. I messed that up. Okay, sorry. P norm of 1.96 is 0.975, and this is our Monte Carlo estimate. Okay, and we're getting something close, right? And this is, again, it seems silly, but this is effectively the Monte Carlo approach. We're just generating values from some computer, and so we can generate pretty much any cumulative distribution function for any of the functions that we have. We can get a Monte Carlo estimate using any kind of random generator, right? So if we wanted to just say y comes from r exponential, let's generate 1,000,000 values, and let's use lambda equal to 0.5. Okay, we can say, what's the probability that y is, say, less than 1? Okay, we get something around, out of the 1,000,000 y values that I generated, about 40% are less than y. Okay, and we can compare this to the true value, p exponential of using the value 1, where my rate is equal to 0.5. Okay, and so the true value is 0.3934693, and all I'm doing is I'm just, again, if we take a look at the actual values of y, they look like this, and you can ask for a histogram of y, and it looks like this. And we can say, okay, what proportion of these are less than 1? Okay, so this is the actual value, and by comparing how many of our actual values are less than 1, we're getting an estimate for the cumulative distribution function. Is that okay? And basically, again, I'm asking for the mean of And effectively what's happening is when I do y less than 1, I get this logical vector. R is coercing this, right? If I do as.numeric, we get zeros and ones, which is pretty much what the indicator function is doing. And then we're asking for the mean of this, because this is pretty much my function. Okay, so it's just a sample proportion of successes in n trials for whatever random thing we did, okay? This, here I said I'm going to generate 100 million values. 100 million values. And then I'm going to say, all right, I want to figure out what proportion is less than, so Q norm, 0.5, 0.75, 0.8, these are the boundaries, the z-scores. So if you want 50%, you'd use z-score equal to 0. If you want 75%, z-score is 0.6744. If you want 90%, it's 1.28. 95% of 1.6448. 99% is 2.326. And so these are going to kind of form the boundaries, and we're going to ask basically what is the mean of z being less than, say, 0.6744898. Okay, and we get something close to 0.75, not exactly 0.75, because it's a Monte Carlo estimate. And the question is how many values do I need to figure this out? Can I get away with just, say, 100 values? What about 1,000 values? What about 10,000? Okay, and so this is how accurate we can get an idea of how accurate our values are. So the true values, again, are 0.5, 0.75, 0.8. We should be getting this. And if I use only, say, 100 values, okay, my estimates aren't super great, okay? I got 0.52. I coincidentally got 0.75, where I should be getting 0.8416. I'm sorry, where I should be getting 0.8, I'm getting 0.81. Where I should be getting 90, I got 0.87. Okay? But as I increase the number of values that I'm using, so 1 million, 10 million, 100 million, we could see my estimates get closer and closer to the true value, right? As expected. Right? And so things get, especially in the tails, it's hard to kind of express true accuracy out here. But we get something close. We get something close. So where I should be getting 0.99, I get something close to 0.99. And again, this is just one run. If you did it differently, you'd probably get slightly different values. That's what we have here. Okay? So comparison of kind of our estimates versus the actual value here. Okay, let me give you your second view quiz answer. Second view quiz answer is C. C as in cat. C as in cat. I gave you the first one, right? D? Okay. Second one is C. Okay, again, how many values do we need? How many random values do we need to sample to achieve a certain level of accuracy in our estimates? Right? We need to know the variance in our estimates first, and whatever estimate that we're producing, in our case, f hat, okay, and as far as the cumulative distribution function goes, is the sample proportion of successes, and therefore the variance of the sample proportion of successes for Bernoulli is basically just, p times 1 minus p over n, right? So this would be the variance as far as we go. So the maximum variance happens if you have 0.5, and so if we were to kind of be conservative, right, about how many values, like we're going to assume maximum variance, then we would say the variance of any kind of estimator, f hat, it's got to be this or less, is going to be 1 over 4n, okay? And so an estimate of the standard error, is going to be 1 over 2 square root of n. This is going to be kind of our biggest value as far as the standard error is concerned. So the square root of n is factored into the bottom here. And so therefore, if you want to get basically one more decimal point of precision, you need 100 times more values, right? If you want to be accurate to say 4 decimal places, then you need 10 to the 8 values, right? If you want to be accurate to 3 decimal places, then you should generate 1 million values. So every additional decimal place, you need 100 times more observations. And so in that regard, Monte Carlo estimation is not an efficient method. There are ways to improve some of its efficiency deficits, okay? And one of these methods is called importance sampling, okay? And I'm going to just kind of introduce the topic here, and this is a bit of a wonky idea, because it seems like, how could this even possibly work? But it does, okay? And so this is what importance sampling is all about, right? So we're going to go back and we're going to just say, hey, this is the thing that we're going after. We have some random variable x. X is defined by the PDF f, okay? X is defined by the PDF f. We're going to apply an arbitrary function h to that random variable x, and I want to know what's the expected value. That's Monte Carlo integration. And we said we can estimate this, all right? We can get an estimate of this integral just by generating random values of x, okay? So far we've been able to do this. We're just generating random values of x from the computer. And then we apply the function, and then we take the mean. That's all we've been doing. This is everything we've been doing so far. But the question is, what if I give you a PDF and you can't generate values from that PDF, right? So let's say I just give you some arbitrary function, and technically any function, as long as it never goes negative and as long as the integral is 1, could be a PDF, right? So as long as the integral of the entire support is 1 and it never goes negative, then you can have that could be a PDF. So what if I give you some arbitrary function? It's not normal, it's not beta, it's not something that's built into R. And I say, I want you to do this. And you say, well, I can't generate random values from that PDF, right? What if we're not able to generate random values from F directly, right? We can't generate a random sample from this. What am I supposed to do? What am I supposed to do? Okay? The answer is, well, generate values from a different sample. And let's use that. And then let's adjust for it later. And it will work, okay? We're going to perform importance sampling, okay? So, I'm sorry, we've got a couple options, right? So right now, so far, everything we've done is we're just using R's built-in distribution functions, right? We have, R unif, R norm, R beta, R gamma, R exp for exponential, R chi-squared, there's all these different probability distributions that you might have learned about, might have remembered, and we're able to generate random values from these things, okay? But again, we might not have a function that's able to generate these values randomly, okay? So what we can do, one option, we'll talk about this next week, is we'll learn how to generate random values from a different distribution. We'll learn how to generate random values directly for a different distribution, okay? But if you don't actually need samples from a different distribution, like you don't actually need to work with the numbers themselves, you just want to estimate an integral, you just want to estimate this function, what is the expected value of this function, we can do importance sampling, okay? Importance sampling is a weird name. I like to call it weighted Monte Carlo integration or something else. But what we're going to do, again, this is what we want, and what we're going to do instead is we just say, I don't know how to generate values from this thing. You gave me a weird looking distribution. I can't do that. So this is what I'm gonna generate values from G. I know how to do G, okay? I know how to generate values from the normal distribution. Or I know how to generate values from the exponential distribution. I know how to generate values from something else. This other thing makes sense to me. Well, you gave me, I don't know how to do that. Okay? The only requirement, as far as picking some arbitrary distribution G, is that the support of the function f has to be contained within the support of G. Okay? Which is to say that this distribution G cannot be 0 if f is something other than 0, right? So if f is able to generate, like, let's say you pick some distribution where f can produce random values of, say, 2 or 3 or 4, 3.7, okay? Then you can't use the beta distribution as your G, because beta can only generate values from 0 to 1. Yeah, question?
Does it have to work the other way? Like, does everything outside the support have to be 0?
No. Yeah, so f, you can have, so G could go from, say, negative infinity to positive infinity, and f is just defined on 0 to 1. That's allowed. And that's going to be very inefficient, but it's allowed, okay? The only requirement is that you can't, that G is able, theoretically, in theory, G is able to produce any value that f could produce, right? So if f could produce a million, then G needs to be able to produce a million. It could have an incredibly low probability of producing a million, but it needs to be able to do it, okay? It can't have a probability 0. It has to have a probability something other than 0, okay? Okay, so then what do we do? All right, well here I just threw some math up here, and I say, look at this, it works, okay? So the math here says, I'm going to multiply by G over G, okay? This is, so again, this is under the assumption that G of X is never 0 for when we're looking at the support of X, okay, where X is something other than 0, X is always, whenever f of X is greater than 0, right, the support of X, we're assuming that G of X is never equal to 0, okay, otherwise this thing will break down, right? So I'm going to just multiply it by G of X over G of X, right? I'm allowed to do that. And then I say, okay, well, let's just move G of X over here. So now I've got h of x times f of x over g of x. Okay, so g of x, what is g of x? G of x is a PDF. G of x is a PDF. And so now, if I just group this thing over here, what is this? This is it's an arbitrary, but, you know, it's just another arbitrary function, okay? Now it's more complicated. It used to just be arbitrary function h times PDF f, all right? This was the arbitrary function h multiplied by the PDF f, and that would give me the expected value of this thing, okay? Now, I've got weirder arbitrary function. The arbitrary function is h times f over g, but it's still just an arbitrary function. That's the important thing to note. This is an arbitrary function times a PDF. Okay? We're just getting everything into some arbitrary function times a PDF. Okay, and so what is this? This integral, when we do this, this is again in the same form of just arbitrary function times PDF. This will evaluate to the expected value of this arbitrary function, the expected value of h of x times f of x over g of x, okay? Where x is a random variable defined by the PDF g. And do we feel like this would work? So I just put up some letters here, but we're saying, oh, okay, I guess this will work then, right? And we're allowed to do this because for any value outside of the support, okay, for any value for x that's not in the support, f of x is equal to 0. So we're not going to worry about that, okay? So this is going to equal this. Okay, and so mathematically, or just as far as how does this work when we actually compute this out, this is what we do. We say, I've got some function g, and we're going to say, well, I don't know how to estimate g. I mean, I'm able to generate values from g, but I can't generate values from this other thing, f. And we're going to say, okay, well, that's all right. Just generate values from g, because you know how to do that. Right? And then you compute, you apply the function to every value you generate. H times f divided by g, h times f divided by g, h times f divided by g. You do it for all of the values. And then you take the mean. You take the mean of that. And that's it. That's it. Does that work? And again, the implications of this, I'm upset that I can't draw. So again, let's say your PDF is something weird, right? Let's say it looks like this, right? And we're gonna just say, we want to, and we're gonna, and we have some function h of x. H of x is, we're gonna draw a random value from here. Let's say it goes from -1 to 3, 0, 1, 2, something like that, right? I'm going to generate some random value out of this distribution, and then let's calculate whatever value I get, let's square it. And we're going to ask, what is the expected value of random variable x, right? What is this thing? Okay. Well, we could do this easily. If I were able to generate values from this thing, I would just generate the values, I would square them, and I would take the mean. And that would be my answer. Okay. What am I doing now? I'm saying, well, I don't know how to generate values out of here. So all I'm going to do is I'm going to just pick maybe some distribution I am able to generate from, right? So I could just say, hey, let's generate values from the normal distribution. Or any other thing, right? So this is, G is just standard normal. It's probably not good to do this, right? But standard normal can generate any value from -1 to 3, okay, 3 would technically be all the way out here, okay? So we're going to generate values from the standard normal. Sometimes we get values like 3.2, sometimes we get values like -2, okay? That's fine. So we just generate some samples of x drawn from standard normal. Okay? And then what do? I just take, we're going to plug in h, which is x squared, times, and I need to have the functional form of this. I don't know, what is the functional form of this? This has some functional form f of x. So we're going to multiply it by f of x divided by g of x, okay? I can't write with my pen here, I'm so angry. And this thing, this term, this term right here, basically is a weighting factor. It says, when f and g are similar in size, it says, okay, that's great. But there's going to be some places where f is much more likely to generate it, and g is much less likely to generate it, okay? In those cases, we say, well, anytime you get one of those values, weight it heavily, okay? And then there's other places where f generates the value very infrequently, but g generates those values very frequently. And we're basically going to say, okay, anytime we get one of those, we're going to weight it a little bit less. So we've got kind of this weighting factor here, f over g. And that corrects for all of the differences between what F would have generated versus what G would have generated. Okay? And so we'll take a closer look at this on Friday. We'll look at a few examples to see how importance sampling works. Okay, let me give you your last view quiz answer for today. Today's last view quiz answer is E. E as in elephant. E as in elephant is your last view quiz answer for today. Okay. I will release homework 2 very soon. And so you can see that, expect to see that posted up on CCLA in the coming days. All right, that's it. Have a good day, and we'll see you guys on Friday.